All righty. Hi, everyone, and welcome to Chapter 7, which is on linear regression and also multiple regression. So linear regression is a way we primarily in business use to try to make predictions or create forecasting to try to predict demand, and then we can meet demand with supply, right? But in reality, it's a way we can view the relationship between any two or more variables. And so what we do is we run it through a statistical process, a specific equation, in order to come up with values that we plug into another equation, and then it gives us a predicted value of what it is we're trying to predict. For example, maybe we're trying to predict how many people go to the water park, right? So here in Tulsa, Safari Joe's or whatever it's called now, used to be Big Splash. They're trying to figure out how many people are going to show up that day. Well, maybe they could take the temperature for the last however many days, whether it was rainy, sunny, cloudy for the last however many days, and then look at the historical record of how many people attended the park those days. Well, if we plugged all that into, if we ran regression on those, we might be able to figure out if any of those variables helped us predict the attendance. That's the predicted value we're looking at. We would get, certain numerical values that indicate a healthier or a weaker relationship between the variables, and maybe we can use that to actually do some good in our business by predicting the demand. We can have supply there, whether that's food or drinks or SOCOMs, or just having enough people on staff in order to accommodate all those customers. Or maybe it means maybe we've got vacation requests in, whether or not we can approve them. Well, we predict that we're going to be pretty busy that day, so we can't, or whatever the case is. It's all about trying to make better decisions in the operation of your business. So we have two or more variables. Like I said, one of those variables is the dependent variable. This is the variable you're trying to predict, because that variable in our hypothesis depends on these other things. There's a number of things that go on to determining how many people show up to our water park this day, right? This is the dependent thing that we're looking at, the attendance numbers. The independent variable or variables are also known as the predictor variables. These are used to try to figure out what our attendance is going to be, or whatever the demand element is we're trying to figure out. There's going to be one or more things that factor into that. And so this process helps us to identify what those things are. Maybe we have a theory that it's the weather. Maybe we have a theory that it's the temperature. Maybe we have a theory that it's the cost of gas. Whatever it is that we're trying to figure out, if that is what's affecting the demand. Through regression, we're able to try to identify that and find the goodness of fit of how well this variable fits the model, fits the prediction method that we're looking at. So in our notation purposes, we use X and Y, and you can, you've seen X and Y before on the scatter chart and other graphs that make use of XY coordinates on a graph. The Y, or the dependent variable, is always noted on the up and down side of it, the Y axis. The independent variable, the things that try to predict what changes, are noted on the X axis, the horizontal axis line. And so linear regression, simple linear regression, uses one model. We look at one independent variable, which is known as X. We assume that change, whatever the changes that are going to affect the dependent variable Y. In multiple linear regression, we can look at two or more independent variables and see how well each of those affects the affects the dependent variable, that y variable. So let's look at the simple linear regression model. There's one equation right here, which is said in a number of different ways. They use this term as well. This looks like a B with a 0 and B with a 1. But these could just as easily use the X and Y letters instead. It's just this is the equation that's set up. So let's talk through this because they use different things here than you might see in other locations as you're looking up the linear regression model. So what they're saying here is that the predicted value of Y, which is usually noted with a little arrow on top of it, the predicted value of Y is equal to the intercept, which is going to be one figure that comes out of our regression, plus the slope of our variable X. And then to that, we can add any kind of error terms. If we know that there's a common error that shows up a certain amount of times, we can add that into it. We're not going to get into that very much, though. Just a random element that changes the predicted value here. So what we need to know is that the let's see here. Yeah, the equation there's just different ways of writing it with this lowercase b, uppercase. I think this is uppercase beta symbol. I'm not entirely sure, but seems reasonable that is. Different ways you're going to see this written, but effectively the same thing. You're looking at the intercept and the slope of the first X variable in this. So let's try to make this make a little more sense. Here's another way this is written. Why is it written this in many different ways? The main idea is that the predicted value of something is going to be equal to the intercept plus the slope times the X value. So how do we use that, right? Intercept, think of it like a baseline. Once we run through regression, we're going to say, we're going to have a baseline, attendance of 100 people, okay? So the intercept might spit out 100 for that value. And then the slope might say maybe 1.5. So the prediction is going to be 1.5 people for every change in the temperature. Maybe the X variable is a temperature. So once I have the intercept, I've got this one number in mind, right? It's 100. And once I've got the slope, and the slope is 1.5, well, what I can do is I can say 100 plus 1.5 times the temperature, right? So the temperature is 75. Then I do 75 times 1.5 and add it to 100. And that's the predicted value of Y that day. So I'm just plugging it into a very simple, it turns out, algebraic equation. And as you see these practice problems, that'll start making a little bit more sense. So, I think repetition is key on this kind of thing. You're going to see it, you're going to see it again, and then eventually I think it'll click for you. But we just plug in the values, and these values, fortunately, I'm not really going to have you do a lot of the hard math with pen and paper on these. I'm going to have you be using Excel for these to have it spit out the value of the intercept and the value of slope. You can be using the data analysis tool pack in order to generate these for ourselves, and then plugging them into the formula to make a prediction. All right. Yeah, I don't think we're going to need. Okay. This is we've seen this here. If we plug this into a scatter chart, these X and Y coordinates, we can see this line. The scatter chart is going to be very important on this chapter as well. But the regression line, if it's a positive linear relationship, you'll see it as X goes up, then Y also goes up. Whereas as X goes up, Y goes down, that's a negative. And then no relationship would be, a flat line, or just kind of, the regression line will be here in the middle, but the dots could be everywhere. There's seemingly no trend whatsoever. That would indicate no relationship between the two variables. So either if you add the trend line to your scatter chart, you see it going up and sloping down, which is negative, or right, middle-ish, because the dots are just all over the place. The least squares method, I'm gonna introduce you to it so you kind of understand it. But fortunately, we're not going to have to do, again, I'm not gonna have you do a lot of the heavy math on this chapter, because we have things like Excel that just give us the values and then we can go from there. But it's a procedure for figuring out the slope and the intercept, ways that we can calculate slope and intercept in by hand, which is it's just a long process that I don't think that I'm going to have you guys do. But I want you to be aware of these terms. Least squares method is a procedure for using the data to find the estimated regression equation. Again, the regression equation is that predicted value of y equals the intercept plus slope times x. So the slope, this b1, is the estimated change in the variable. So slope, why is it called slope? We can see it kind of slopes, right? It slopes positively, negatively, or not at all. When there's no relationship, if there's truly no relationship, you'll see that the slope is 0. Otherwise, it's said to be negative or to be positive. So here's, what these X and Y's are listed at. You have travel time and miles traveled. You might think, well, how many miles you're traveling should roughly match up to the travel time, unless they're going on different routes, in which case the stops are different. But you can see there should probably be a pretty positive trend. You would think that the further you travel, the longer the time. It should be pretty positive, right? If I travel 100 miles, it should be longer than if I travel 50 miles, logically. But maybe these are back roads and not highways, or whatever other reason they're not. But you can see all of these observations. This first number here, driving assignment, that's just a label. This is not anything quantitative that you would ever include. On a scatter chart, you're only going to have 2 variables, and they're going to be quantitative variables. So you map those out, and you can see, not a super strong positive relationship, but it is still, it's worth pursuing. So the first step in determining whether you're going to try regression is to use a scatter chart. If you don't see any kind of trend, positive or negative, then there's no reason to proceed. You would not run this through the regression process in Excel or by hand if these dots were all over the place. But because we do seem to see that the longer you travel on the X, right? So this is the independent variable that's affecting the Y. The more you travel, the longer it took to get there. Then that does seem to coincide. It's sloping upwards. And so there's a positive relationship. We would then proceed and try to figure out what the value of X and Y is. So this least squares equation, I want you to just don't panic, because we're not going to be finding it this way. But I need you to be aware of it for terminology reasons, and if it asks you about least squares method on here, but just know it's a method for finding the regression equation. We're going to be finding the regression equation using Excel tools in this class. If I ask you to predict something and it's not in Excel, you're going to probably be given most of the stuff you need, and the amount of math you have to do is going to be very minimal, but it will not be what you see on the next few slides. So I'm going to kind of skip through them pretty quickly. I'm going to talk about residuals. Residual is every time we have found the regression equation. So we found the regression equation. Now we're going to check all of our past data to see if I plug in last month's observation, the X value from that, into this regression equation that I've just generated. Does the Y value that it spits out, how close did that get to the actual Y value from last month? And however far it's off is known as the error, also known as the residual. Residual, think leftover, right? So how far did it deviate, either positive or negative, from the actual value? So if my regression equation predicts that it would have been 200, but it was actually 190, then the residual is 10. And the residual is looked at as a whole number. It's how far off was it, not negative or positive typically, but the residual is 10. It was off by 10. So you'll need to know that term, residual. That's still going to come up. It's this method we're not going to be exactly using. All right. So when we ran through and found these values, it gave us a value to intercept. So this 1.27, that's the value of the intercept. That's your baseline. We start with that and we add to it the slope times whatever x is. Okay. So if we know how far are you traveling, we should be able to predict how long is it going to take you to get there. So if I plug in 100 miles into this equation, I would do 100 times this, and then add to it the baseline, the intercept value. So whatever the x value is I'm using to make the prediction, times the slope plus the intercept. And you can see I'm working backwards because that's the order of mathematics. And I've always thought that those should just be reversed because you're gonna do this one first because please excuse my dear Aunt Sally, parentheses, exponents, multiplication, division, addition, subtraction in that order, left to right. So you would multiply the x value, however long you're going, times the slope, and then add to it the intercept. And that will give you a prediction. Now you can go back to, this value and say, okay, well, if I plug it in and you can see this time I traveled 100 miles and it took me 9.3 hours. This time I went 100 miles, it took me 6.5 hours. Look at it. And this time it took me 8.9 miles. How far off am I on this if I do 100 times point? So let's see. I'll just get a calculator out real quick. All right, here we go. So 100 times 0.0678 plus 1.2739 equals 8.05. So it should take me 8.05 hours. Okay. And for the most part, it took me a little longer, 9.3, 8.9, but because of this, it brought down that equation value, that slope value, which means that my residual is going to be off by, 1 point something, a little less than 1, and then off by nearly 2 here. But it gives us the best approximation we could have. So that is how the regression line works. Experimental region. So the values of the independent variables, this is everything you've used in order to make the model. So we only had 10 references. The region of those values, the range of those values is all we use to make them, which means it's imperfect. It doesn't have every observation ever. It only had however many we entered into the model. Sometimes we could try to predict the value of the dependent variable outside of this region, which is known as extrapolation. We could say, well, based on this, and this, we could probably say that if we went this many miles, it would still hold true. But we didn't have anything above 100 miles traveled. If we're trying to predict it for 300 miles, it may get way off. If we try to predict it for 5 miles, when the lowest was something like 60 miles traveled, it may get way off. It may not hold true outside of that range. This is how it would look. Pardon me. We plug in our intercept and our slope that these values spat out, we would see that every time we travel 100 miles, we get that 8.05 that I just got on the calculator. If I plug in 4.8, I'm sorry, if I plug in 50 into the same one, I should get 4.66 as my estimate. If I plug in 80 as the x value, again, 80 times the slope plus the intercept, I'm getting all of these, and you can see how much was the error. The errors will all sum to 0 as you go up and down. They are positive, negative, but typically we look at we square the errors, and we square the errors to to smooth it out a bit, and also to eliminate the negatives values, because if you multiply two negatives together, you get a positive number. And so it just makes it easier to view the whole thing. Now you could use the absolute value of the error. Absolute value just means you ignore any negative or positive sign and just look at the number itself. Again, we're looking at how far off was our model. This helps us to determine, if we looked at this model versus another model, how far off was that one? If we said, well, maybe it wasn't the miles traveled, but maybe the miles traveled on highway roads, or the distance from some center point, or some other prediction, maybe it has a lot less errors and does a better job of predicting how far our travel time was. This is just a image which shows all of our predictions along this slope line, whereas the dots are the actual values, I believe. All right, least squares method. So there is a so in Excel, and we'll have a video going through it where I'm going to go through it step by step. But in Excel, after you do the scatter chart, you just add a trend line. And that's going to just display automatically for you. We'll be doing that a lot before you proceed with creating the entire regression model. Again, the first thing you're always going to do is plot them on a scatter chart. Do you proceed or not, right? And then you want to add that into it just to see that sloping. All right, now let's talk about how well this value fits. So if we were to sum up the squared errors, you get the sum of squares, also known as the sum of squared errors, which is why the abbreviation is SSE. That's the sum of squares due to errors, I think is the actual, sum of squares due to error. But I usually abbreviate as, or say it as sum of squared errors, because then it's closer to this acronym. Don't worry about this A value. What this is 8.02. If we look back on our table from a few spots back, you can see this was plugging in our model into the historical data. We can see this is what we predicted. This is what our actual was. I was off by 1.24. Square this value, write it down, and then do that for all 10 observations, add them together. The sum of your squared errors, 8.02. That's what it's talking about. So that helps us to identify how well the fit is of this model. If I have other options that create a lower squared error value, then it's likely I should probably go with one of those instead. Total sum of squares. So, give me 1 second. All right, so the sum of squares total is going to be the squared value of the difference between the y value for any given observation minus the mean of all the y values. So all of the y values on this chart, if we look at them, to find the mean, we add all of them together and divide by the number of observations. The mean is the statistical average, right? So add them all up, we get 67. There's 10 observations, so 67 divided by 10 is 6.7. Now, how far is 9.3 off from the mean, 6.7? 9.3 minus 6.7 is 2.6. 4.8 minus 6.7 is a negative value. Negative 1.9, and so on. For each of these, we do the same thing we did before. We square them. What we get at the end is 23.9 if we add all of them together. So this is this value squared, and so on. And at the end, we get 23.9. This is the sum of squares total, SST, 23.9. There is a relationship between the sum of squares total, the sum of squares due to regression, and the sum of squared errors. And that relationship is the sum of squared total equals the sum of squared due to regression plus the sum of squared errors. Now, in that, in the previous couple of slides, we found that the SST was 23.9 and the SSE was 8.02. Well, knowing that the SSE plus the SSR equals the SST, I can figure out the sum of squares due to regression by subtracting the 8.02 from the 23.9. And that's exactly what we have. Actually, it doesn't show it on the slide. So let me just pop up the calculator again. So if I know that one value is 23.9, the sum of square totals, and I know that the other value is 8.0288, then the sum of squared due to regression, the SSR, is going to be equal to 15.87. That's the relationship between these values. So the sum of squares due to regression is going to see how much the predicted value of y deviates from the mean. So sum of squared error is the predicted value minus the actual. That's how far it was off. That's the SSE. The SST is the actual value minus the mean. So how far was that off? And then finally, the SSR is the predicted value minus the mean. So that's the relationship between those values. These are used, again, to find the goodness of fit. You're looking for, in all cases, lower is better. But knowing that, we can find other items. These numbers are used to plug into other equations to try to figure out overall goodness of fit. So we found all of these values. There's one particular term you're going to see come up, and that's called the coefficient of determination. The coefficient of determination. This is ultimately used to evaluate the goodness of fit for the estimated regression equation. So if what you'll see is that this is also abbreviated as R squared. You'll see it listed as the R squared value. If you take the SSR and divide it by SST, you'll get R squared value, okay? If you have any two of the three between SSR, SST, and SSE, because of the relationship here, you'll be able to find the third one. So if I give you the SSR and the SST, you could find SSE by just moving around the things like you would do in basic algebra, right? You know, if this plus this equals this, then this minus this equals this, or however you need to rearrange it to find the missing ones. Once you've found that, you can then plug in the SSR and the SST. This divided by this equals the R squared value. And it turns out that the SSR we found to be 15.87, 2 divided by 23.9, we get a 66.41 as our R squared value, the coefficient of determination. How do we interpret that? Well, the higher the better here. What this is telling us is that 66.41% of the total sum of squares can be explained from that regression equation. That means that that one variable that we've used, how far you've traveled, accounts for 66% of the variation. Something else out there is making another determination on why why it took us this long, other than the distance traveled, but we've explained 66.41%. So this is pretty good explanation. Probably there's not going to be any single variable that does better than that, but there is something else out there that's explaining part of it. Coefficient of determination, that's the term, also known as R squared. When we're using Excel, you're going to see that listed as the R squared value. All right, multiple regression. So let's talk about this real quick. Let's talk about multiple regression. When we want to include multiple potential independent variables to determine if we can create a better model, then we still only have, we'll only ever have one dependent variable that we're trying to predict. And it might be distance traveled, demand, whatever. But the intercept, you're only going to get one intercept form. However, you're going to get a slope for each of the variables. So a slope for the first variable, this might be distance traveled. A slope for the second variable could be a binary variable like diesel or unleaded gasoline. A slope for this one, whatever the other variable, distance from the hub, size of the tire, how much was on miles traveled on highway road, whatever the case is that we're trying to plug in to figure out how long it took for these trucks to get to where they're going. We get a slope for each one of those variables. We use the same least squares method, but again, when you see the Excel video, you're going to see where these numbers get spat out in Excel. We're going to skip because we're not using that method. When you write it all out, you're going to have intercept plus slope times x plus slope times x2 plus slope times x3 and all the variables therein. That's what here. So if you had two variables, multiple regression of two variables, you're going to get one intercept value. Here we go, distance traveled, and they give number of deliveries as the second example. So we get a slope value, and then you plug in distance traveled, 50 miles here, number of deliveries, you plug in 5 here, and then multiply it times your slope plus this one, add it all together, and you get your predicted value of y. How long is it going to take? Estimated travel time. All right, after that, it gets into where we're going to go. So the data analysis tool pack you're going to need to use on the Excel video, I'll show you that. I'm going to pause for 1 second to see if there's more information in the slide that's not Excel related. Otherwise, I'm going to save it all for the Excel video. All right, let's get into some terminology here. So statistical inference, we're inferring that or drawing conclusions about one or more characteristics of a population based on what we've drawn from that. This could be the parameters. If I've drawn samples from all of the truck deliveries, I could make an inference that the trucks that we use don't travel much more than 100 miles, or we travel at least 20 miles, or whatever the case is. Based on the data I've pulled from my sampling, I'm using that to try to infer on the entire population and then design my hypothesis based on that, on those values. And there, I skipped the Excel parts of it. Yeah. So there is a way that we write out these hypotheses. We write them out to say that we are hypothesizing that this has a statistically significant determination on the y value, and then we test these, and based on the confidence level we're testing at, are going to either reject or accept a given hypothesis. So if the hypothesis equals 0, then if the slope equals 0, there's no linear relationship. If the slope does not equal 0, there is a linear relationship. So if it's at 0, we say that that was like when the slope was flat, right? There's no relationship between them. If not, then there is likely a linear relationship between two things. The t-test is the name of the test we use for that hypothesis. We're not going to be really using that, but we use the t-test to test hypothesis that a regression parameter is 0, to test whether or not we're going to proceed with the causal relationship between two or more variables before we proceed with the entire regression process. So we use the t-test for that. This is more of a definition thing for you. Confidence interval, that's the estimation that we will find a certain value within within the parameters of that population. So how confident are we that if we, given the data we pulled, that we're going to find a certain value within it? Confidence level is going to be a value, a statistical value of what it is we are, how sure I need to be before I proceed. Typically, and even Excel, 5% statistical level of significance is going to be tested for. And so if we get a confidence value of 95%, and that's going to fit within that difference between 100% and what we're testing at. So the level of significance is going to say 5%, and I need to be at a confidence level of 95% at least in order to proceed. Otherwise, we say that it's probably not statistically significant in our findings. So that's going to make more sense when you see that in Excel and you see the actual values of it. Non-significant independent variables. So sometimes a model improves if we take out insignificant independent variables. Let's say we were using multiple regression and we find that some of the variables are not significant. They don't fall within that certain p-value. It's called, you'll see that in the book, but the p-value listed at below 0.05 to see whether it fits in that confidence level ratio that we're accepting. And if your confidence level needs to be at 99% because of something that has to be very specifically precise, then maybe you're looking for a p-value of below 0.01% instead of 0.05 because of a level of confidence that you need in that product or in the results. But typically we would probably exclude those from the rest of the model altogether and not proceed unless we have a reason to maybe gather a new sample to see if there was some kind of specific outlier. Multicollinearity, that is how much correlation there is among those independent variables. So if I'm doing multiple regression with 4 different variables, I'm going to test multicollinearity to see how well those correlate with one another, because if we're making a model, we want that model to be usable as possible. And if there's 2 of those 4 variables that are basically telling us the same thing, right? Was it rainy or not? Was it cloudy or not? Well, those are probably going to tell us, probably going to have close to the same results on our outcome if we're talking about an outdoor venue of some kind. Maybe we don't need both of those in our model. Maybe cloudy would be good enough to make the determination. If it's not sunny out, then no one shows up to the water park, right? But we're trying to see, is there maybe too strong a relationship between those independent variables? If so, we could probably have a better, easier to use model if we eliminated one of them. All right. F-test is the test where we look at the p-value and look at the probability distribution. That's going to ultimately determine whether or not we accept our hypothesis or reject it. Our hypotheses being this independent variable has a statistically significant impact on what we are predicting or not. Based on that F-test, where we look at what's called the p-value in Excel and in these, you're looking at that value and testing whether it's small enough that fits within the gap you're looking for on your confidence levels. If so, then we can reject the null hypothesis that there is no relationship and accept the hypothesis that there is a relationship between those 2 items. This should start jogging some memories of your business statistics class. We can go ahead and skip that one. Categorical independent variables. So sometimes we can use categorical variables, which are going to be not quantitative variables. These are qualitative variables or categorical variables. Was it rush hour or not? We can assign a binary number of 0 or 1, Was it cloudy or not? 1 if cloudy, 0 if not, or 0 if cloudy and 1 if not, or whichever way we go, we define that. But we can assign a binary variable and plug it into the same equation. And then we just pop in 0 or 1 into our regression chart, and it works the same way. Probably not as well because we don't have a lot of variability there. We don't have a lot of room for little differences like we might have in miles traveled, 70 miles versus 80 miles versus 90 miles versus 100 miles. Was it rush hour or not? Well, it stands to reason if it's rush hour, you're not going to travel as far. So it does help. If we can add that to it, you have the potential for improving the model with that dummy variable. Potential for improving the model, not a guarantee, but you'll measure that goodness of fit, that R squared value, the coefficient of determination value, to see if that did have a effect on the goodness of fit of the model or not. And then, all right, more mathy stuff. We'll come back to those. We can include 3 different states of being, such as cloudy, rainy, sunny. Those can be 3 different things. When we do that, we have to have 2 variable rows. So k minus 1 means however many steps there are. If it's cloudy, rainy, and sunny, we need to have 2 different variables. And one is going to say, was it sunny? And then 1 if yes, 0 if no. Was it rainy? 1 if yes, 0 no. And if both of those are 0, then we conclude that it's the leftover one, which I think was cloudy. I think I said sunny, then rainy. So if both of those are 0, then it's the third thing, which is cloudy. And that's how binary works, right? You have on off switches effectively, and if both of them are off, it's the third thing. And the third thing would be the default of cloudy, right? And so maybe not those ones making the most sense in that case, but that's the idea. You can make these more complicated. We won't see that as much, but that is something that may come up for us. And then as far as modeling them goes, more Excel stuff, and back to the next step, which is going to be some terminology. There is, all right. Not the value of the independent variable at which the relationship between the dependent variable and independent variable changes. So every once in a while, if you go too far, something happens. Here's a good example of what that could be. This really screws up the model when there's a not in it. This says, how long was the person employed? Well, they're selling, they're doing great, but around this point, they just get burned out, and then they just start not selling as much. So that's what's happening in this model. The not is the point at which that regression line changes directions. So approximately 90 months, it breaks the model, and we could say that maybe by then we need to look at moving these people into a more exciting role to keep them energized if they're good employees. Dummy variables, we'll work on that when we actually do the work of it. Interaction. So this would be if you have one of the variables getting to a certain level, like in that not, then it changes the entire interaction between the first one. So we're going to go ahead and not do the nonlinear relationships, but I want you to be aware of that term in case it comes up in the future. There's a quadratic formula we can use, which uses polynomial variables. We're not going to probably do any of that mathematical work here in this class. I think that's a little too advanced for a more general analysis class. Model fitting. So basically this is, we are checking for how well variables are working out in a model. The summary of this is that we can slowly add more to our model. We could start with all of them and remove some. But if we run this model several different times with several different variables included, we're going to get a different R squared and R value. And eventually we'll end up with one that's best, but we can evaluate them as we go to see which ones are more likely for replacement. So this is, basically which step do we include or remove certain variables from our model, or add new ones to that. So working backward, working forward, let me stepwise where we're doing more than one. Oh, well, here's the definition of that. So first step, whichever one best satisfied is added to the model, and then each remaining one is then added to see how much it changes it positive or not. So basically you're adding one at a time until your values stop being significantly improved. Backwards, you are removing ones that don't have a high enough p-value. Stepwise, you add the first one, and then the remaining ones are evaluated and independently they're evaluated, and then you're adding that one into the model instead of just adding each of them into one at a time. You're independently evaluating each of them and then adding those to the model to see if it improves. It may not, because it may be redundant. And then I think the last couple terms, overfitting. You've created an overly complex model for no good reason. Basically, that's overfitting. There's a little more to it than that, but overfitting can mislead how well you can be predictive. It's too precise and would not work in a broader sense with other variables other than what you used in your test set to test it out. You can avoid this by trying to find independent variables that will have meaningful relationships, not just ones that had made a change or happen to coincide, but ones that can have an effect. Don't just let the software dictate. Try to use your knowledge, your gut, your experience to try to guide how you develop your model. And let's see, last couple slides, here we go, almost there. All right, so a couple of terms you need to know, one being training set. This is going to be the initial data you use to build the model, and then validation set, you get more data and see if it still worked and worked just as well as before. That's training set and validation set. Holdout method. So the sample data are randomly divided into mutually exclusive training and validation sets. So you take all of the data at once and you just split it up evenly. You don't just pull for new ones. K-fold, so number of equally sized mutually exclusive ones, and these many iterations are executed. You're basically making several models at once and then validating against one another. Leave one out, cross validation. All right. Same thing as before, and then whichever one you left out, so you make a bunch of ones all at one time, and whichever one you left out you use. But really, you need to know training set and validation set out of those things. Training set is, the idea is you want to make sure that it wasn't just a total fluke that you happened upon it being statistically significant or not. All right, little complicated chapter compared to some of the previous ones, but once we do the Excel practice, I think this is going to make a lot more sense when you see these theories with actual numerical data included in them. All right, thanks everyone. Hang in there.